Do you see my screen now?
Yes.
Okay, great.
Yes, doctor.
Now we already covered all this. And we have a lot of equations here and there, Barks transformation. I think we stopped at this one. So Barks transformation, as we mentioned earlier, there's some kind of transformation from ABC to DQ or zero DQ. So this is the flux linkage, which is equal to L multiplied by the currents now in DQ frame. This is the stator, and these are the field Dunbar winding in direct X, and then this is in quadrature X. So you have here L0 is defined as such, and this comes from the Barks transformation. LB, LQ, and this is the factor K here is square root of 3 over 2. And transforming the state of currents and voltages, we can write this as we mentioned earlier for the voltage before IABC equal to the Bark transformation, the inverse of V multiplied by 0 dq. And the currents are the currents here, and this is the unity matrix or identity matrix. And voltage, we can write the same equation. And substituting into original equations of voltage, if you still remember the first equations of KCL voltage written at the beginning, you can replace voltage ABC if dq by this 0 dq here, and also the currents IABC, IF dq can be replaced by this, and the flux linkage also can be replaced by this. And flux linkage equal to L times the current. So if L is varying, then you can have the derivative of L times current and so on. So of course you can multiply by the inverse of this, which is BU. So you can have it BU here. This is the inverse of this. As we mentioned earlier, the Barks transformation matrix is orthogonal. So B inverse equal to B transpose, and then you can have this here, multiply this equation, and also multiply this by this term. So you can simplify these equations to the voltage here equal to the resistances multiplied by the currents, and you have here d by dt you can have here, if you multiply these two terms together, this one, so you have b d by dt, b inverse here, times lambda minus dt. So this is d by dt b inverse plus b inverse times this vector, and b inverse multiplied by d by dt of this vector. So you distribute the derivative over these two quantities here. So you have here b, the derivative of b inverse times this, and when you have b times b inverse, it will be identity matrix. So it comes here to d by dt times the flux linkage here. So of course d by b inverse by dt, b is a function of theta, so you can get the derivative of d theta by dt times d by d theta b inverse. D theta by dt omega, the speed, and you can have this simplification. So d by dt b inverse, this is b inverse, and when you have d by dt, you can have such equation. So you end up with this, and when you multiply these two matrices, you end up with this matrix at the end. So if you replace b d by dt b inverse, you replace it here, multiplied by lambda 0 dq here, and minus d by dt. So you can have these matrices. You have here v0, vd, vq, and vf, and there is no voltage in the damper winding in dx, and this is the equation on damper winding of qx. So how many equations do we have now for this? This is the let us say fifth order. If we remove this equation, and let us remove this equation, and if it is balanced, this is isolated. In this case, you have like a fifth order model of the synchronous machine. This is called flux linkage model. So this is flux linkage model. So you have the states here is flux linkage of field winding, damper winding, and flux linkage here in dx, and flux linkage in qx. So these are the states. So this is the fifth order model of synchronous machine. So this fifth order model represents the electrical part of the machine. If we add the swing equation to this model, so we have seventh order model of the synchronous machine. And of course, this is the voltage, and this is the flux linkage. We can write this model in terms of the currents. If we have L is constant, inductances are constant, then we can replace lambda by Li, and you have here Li di by dt. So L is constant, so L will be here di by dt, and in this case you have the current model, not flux linkage model, but you can replace it by current model. And the relation of the current and the volt and the flux linkage is given here in this equation. Here it is. So you can express lambda f, and you express it in terms of the currents. So you have the current model. Current becomes the states. So based on these equations, we can write or we can develop the following equivalent circuits. This is in the D-ax equivalent circuit. This is a Q-ax equivalent circuit. And this is the field winding. This is a Dunbar winding in direct X, and this is Dunbar winding in quadrature X. So as you can see here, you have here omega lambda Q. This is called speed voltage or inductance voltage, speed voltage, lambda, omega times lambda Q, and we have here omega times lambda D. So these are the equivalent circuit of the machine, and these are the flux linkages as you can see here. In terms of currents, the above equation can be written as such. So if L is constants, we assume these are constants, so it becomes L di by dt, and this is the L di by dt. So this is becomes the 7th order model of the machine. Of course, you can eliminate this. You have 5 states here, and plus the swing equation, which have 2 states. In this case, you have the 7th order model of the synchronous machine. Of course, this is not the only model for synchronous machine. We will not, actually in this course, we will not work on the 7th order model, but we will simplify probably in the next material or next handout. We will discuss the different models of the synchronous machine, starting from the 2nd order model, which is commonly used in transient stability. If we add the flux or the voltage VF or the field voltage or field winding, if we add the Dunbar winding also. So we can build the 2nd order model, or we can have 3rd order model. We can have 4th order model or 2-axis model, and we can have also 7th order model. So these are the models that we can have for synchronous machine. Keep in your mind that this only for synchronous machine. We didn't include any exciter modeling or any governor modeling or mechanical part modeling. This this is only the synchronous machine. We have a question from Saad Ahmed, please.
Yes, Doctor. I am a little confused about the meaning of order. Do we just mean states?
States, yes. Number of states.
All right. Okay.
Number of differential equations that we have.
Okay.
We have here di d by dt, diq by dt, dif by dt, and so on. So we have here, as we mentioned, this is isolated. We will not consider this stationary reference. So we have 5 states here, in addition to the swing equation. So it becomes 7th order model. Now what we will do later, we will simplify this. We will see if swing equation, and if we consider only the field voltage, and if we this becomes the 3rd order model. If we consider the internal voltage in Dx and the Qx, so this becomes the 2-axis model, and this is the 7th order model or the flux linkage model. Okay, so we will see in next hand out the different models of synchronous machine. Actually, in this course, we will focus more on the third order model. And we have, in addition to swing equation should be there in any way. In addition to swing equation, we have the internal voltage equation, which depends on the field voltage. So we consider the field here. Okay, so we have now the third order model. So we will see this in details later on. The voltage equations have constant coefficients provided that the speed is assumed constant, and the equation of V0 is not coupled to other equations and can be treated separately. And this gives you the synchronous generator representation or modeling, the electrical part of the synchronous machine. Do you have any question? Hussein?
Yes, doctor.
Yes.
I just wonder about the zero. We were saying that we have direct and quadrature and zero. Is this zero axis equivalent to the zero sequence component in the
It is
symmetric?
not a zero sequence component. This will appear if we have unbalanced condition, which is, and you can say it is very, very rare. As you can see here, this is V0 equal to R times I0. There is no coupling with any other current. And also L0 di by dt, all these coefficients are zero. But this is like a separate circuit. Okay?
Okay.
And if we have, as we mentioned, balanced, so this becomes zero. So, is it clear, Hussein?
Yes, doctor.
Any other question? Ayub, Horani?
Thank you, Doctor. Doctor, here we have derived the flux linkage model, but here we relate it to the transient fault. So, but during the transient, we said we only study the first or the second cycle. So here the field time constant. How do we deal with such? So what kind of fault that? So I'm honestly bit confused.
Again, you want to ask about?
Yeah, here we have derived the flux linkage model, right?
Yes.
And the flux linkage model, includes the field also.
Field winding,
but
yes.
yes, but we said earlier, the field time constant, we assumed it will not change, within the few first or second cycle of the transient. So how this relate with the transient and the field?
You are right, but this depends on your stability type that you want to investigate. And for example, as we mentioned earlier, in transient stability, which is you can say transient stability, you need like one cycle after the fault. So one cycle after the fault, in this case, the field winding or the time constant of the field, which is called the O prime. This could be about 6 seconds. So the field winding or exciter circuit will not change the field winding voltage in this very short time in millisecond, 16 millisecond or so. So in this case, if you are addressing the machine, or you want to study the stability of the system within this frame, as we did before, we have only the swing equation. Second order model is enough. If you want to simulate the system for 5 seconds or 10 seconds or 20 seconds, in this case you have to take the field now will play a role in this time period. So this is the 7th order model, and we have the 7th order model. But it depends on our study. We can have second order only. We can have third order if we simplify, if we approximate something. We can have fourth order, and we can have 7th order if you need more detailed analysis. You can have the 7th order. Yeah, it is some kind of approximation, Ayub. You can have the 7th order if you need detailed analysis. If you have a very short time after the disturbance, then you can neglect all and you can have only the swing equation. For example, if you have here for the third order model, we consider the internal voltage in quadrature X. In fourth order model, assuming that this is EQ prime and we have ED prime equal to 0. And if we consider ED prime, so we have the fourth order model, and so on. So this is the model, this is the detailed model, and depends on your study, depends on the simulation time that you need to investigate the stability on. You can approximate this 7th order model to any other model or lower order model. Did I address your question?
Yes, Doctor, very clear. Thank you so much. But I was a little bit confused because we started, this synchronous machine transient analysis. That's why my question. But it's clear now. It's clear. Thank you.
احنا what we considered so far transient stability, equal area criteria, numerical integration, and so on. So we developed the swing equation. Now, if we need to study the dynamic stability for longer period, 5 seconds, 10 seconds, in this case, you can either you approximate to lower order, or you can consider the 7th order model here. You have 5 differential equations plus the swing equation. Okay, so let us move to the next. Yes, synchronous machine models, in which we will see the, as we mentioned, second order, third order, fourth order, and that one which is the 7th order model. We will introduce here the per unit quantities. Per unit for the reactance, per unit for the inductance, per unit for the speed, and so on. All the quantities, voltage also, per unit quantity for the voltage. Equivalent circuits of the direct X and the quadrature X. Reactances and time constants of the machine. And the second order model, third order model, 2 axis model, or fourth order model, we call it. And seventh order model or higher order model, which is a seventh order model that we just developed now. So the following equations have been derived earlier. These are the 6 equations of the electrical part. Neglecting this, so we have 5 differential equations here. And in terms of currents, and the above equation can be written as we did also in last handout. You know, these are the voltages, and now instead of flux linkage, we have the currents here and the as the states. So let us start with this extensive model, and we will see the how to derive the third order model and the fourth order model. Second order طبعا is straightforward. This is just swing equation. So virion quantity, assume the synchronous speed as at the base speed omega b. This is the base speed. The synchronous speed omega b equal to omega s. We have 377 radian per second. Okay, so this is 2 by f. Omega the rotor speed. Of course, omega embryonic equal to the actual value over the base value. So just straightforward. VB equal to the base resistance times the base current or base impedance or base inductor reactance. VB equal to also omega times lambda. So this is also V base equal to this quantity, and X equal to omega L. Of course, X equal to the reactance equal to omega times L. So X base equal to omega base L base. And if you want to get the X embryonic, you just divide the omega embryonic times L embryonic. And if you consider the omega is almost constant, so omega over omega b approximately 1. So in this case, the reactance embryonic equal to the inductance embryonic. Okay, X embryonic equal to the inductance embryonic. Also, lambda equal to Li, and L base equal to L base I base, and the flux here embryonic equal to L baryonic I baryonic. This is also the flux. This is the flux linkage, and this is the flux, but embryonic. But this is embryonic. This is psi embryonic flux. So it is x times I or L times I, and this is approximately equal to x times I. And finally, torque equal to B over omega, and if omega is approximately 1 baryonic, so torque embryonic will be equal to torque base equal to power base times over omega base. And if you divide, then the torque embryonic equal to power embryonic over approximately 1, so torque equal to power embryonic. Also, BE can be calculated in terms of armature current and speed voltage. As shown, you can have torque equal to B over omega, and this is also equal to this quantities embryonic. So you have omega times lambda or psi embryonic times IQ plus this is times ID, or we can have the torque embryonic as psi d IQ minus IQ minus psi q ID. Or later we will see also in terms of VD ID plus VQ IQ. So this is in terms of voltage and the current. Deriving dividing through various terms by the base voltage of the proper form, then we can, divide all on the V base, all that equations, 5 equations derived earlier over the this, we can have VB, VQ, and VF direct X damper winding and the quadrature X damper winding. Okay, so recall the equations. Here lambda flux linkage equal to L times current, assuming only one common mutual reactance for all windings per axis. And in direct X we have XMD for the direct X linkage. What is the direct X linkage? What are the flux linkage there, or the mutual inductance there? We have the stator and the rotor. You have F, you have D, you have here D and Q. D and Q. So we have here mutual inductance between these at the direct X, we have the D component of the stator, flux winding and damper winding in direct X, and we have Q damper winding and the Q of the stator. We have also mutual inductance here. So we will replace all these. You have MD, MQ, MF, MR, and so on. We will assume that with the direct X we have one mutual inductance, and in quadrature X we have also XMQ, mutual in quadrature X, which is it's okay. So we have here the flux linkage in per unit of psi D, of psi F, of psi D. This is in the direct X. You have 1 over omega 0 XD, the mutual inductance, and the mutual inductance between the direct X and F and D. And you have the flux here for the flux. You have mutual inductance between the direct X of the stator and the field, XF self reactance of the field winding, and the mutual between the field and direct X damper winding, and also for the, and we can write similar equation for the quadrature X. You have psi Q and psi Q capital, which is equal to the self reactance and the mutual reactance between the direct X, quadrature X of the stator and the quadrature X of the rotor. Hussein, please. You have a question, Hussein?
Yes, Doctor. Why do we have negative direct current here in this formulas or equivalent circuits?
This comes from the beginning. This comes from the beginning. If you from the beginning, maybe from the I don't know, maybe in the previous slides at the beginning, when we say when we write the differential equations or the KCL, it's not here. It's not clear here. Yeah. Did you still remember? Should I open it? When we write the KCL, KVL at the beginning, and we see the induced voltage plus RI plus d by dt times Li, this is equal to 0. So we have a voltage on one side and the currents in the other side. So it becomes minus I. And also for this, for the quadrature X again, but for the field, since we have external voltage, so this external voltage equal to the current there. And for the field, for the damper winding, we have 0 voltage. It is short-circuited. So the R times the current plus L di by dt equal to 0. So we have here positive current for ID and IQ capitals. Are you following me, Hussein?
Yes,
We
yes,
should
somehow.
open it again. We can open the previous slides if you want. When we start developing these equations here, in terms of currents, maybe I don't think on the end here. Yeah, I think this is the equations here. Yeah, this one. If you look at this one, you have induced voltage here in phase A. So this induced voltage in phase A, if you apply KVL, so VA, this is induced voltage. This is not external voltage. This is the induced voltage, VA plus R times IA, RAIA. This is for phase A, plus d by dt Li or lambda. This is the lambda A, which is LAIA. So this is equal to 0. So this is KVL. So if you apply this, so VA equal to minus R here, R minus here, minus R times IA, minus d by dt times lambda A. For the voltage, and the voltage you have external source here. When you apply KVL here, you can write minus, you apply KVL in this direction. So minus VF plus RF IF plus, if L is constant, so it becomes plus LF di by dt. But if L is varying, so we can take the derivative here of lambda F. So if this is equal to 0. This is KVL. So in this case, VF will be on the other side, and these are minus again, or you can have VF is positive, and these will be also positives. Am I right? So you can check here.
Yes.
The IF and the IA, مثلا. And also for this, of course, this is R times RD, IRD capital, ID plus d by dt lambda d equal to 0. This is the KVL here. So you can see here the signs are positive, equal to 0. And then here, if you take the VA as, on the other side, it becomes negative. Did you get the point?
Yes, sir.
So this is the equation.
Thank you.
I'd like to close this one. Give control presenting what is. I would like to this is one. Close it from here. The mouse is not. Okay. So let us go back to Ken. So we are here, right? So these are the equations, and we can express them, and we cover this the unit. So if we replace, if we have only one mutual inductance between the direct axis and stator and rotor, so this becomes the flux linkage of the direct axis, field winding and Dunbar winding in the dx, and this is also the flux linkage of the Q in the stator and also Q in rotor. So where minus ID on CD due to armature reaction. So these are the voltage drops here. XD, XF, XD, XQ, XQ are the total reactances of the respective winding, or the self reactances here. XMD, XMQ are the mutual reactances of the respective axes. So usually we can approximate the winding or the equivalent circuit in the direct axis as such. This is like, it is not a physical connection between these, but this is just an approximation. You have here field winding, and this is the field winding. This is the Dunbar winding, and this is the mutual between between the direct axis inductance, and this is the leakage reactance, leakage inductance of the, or leakage reactance of the stator, and this is the resistance of the stator. So these are the three circuits of the direct axis. And also for quadrature axis, we have the mutual inductance, and this is the leakage of the stator, QX, and this is in the direct axis. And this is the Dunbar winding of the rotor in quadrature axis. So XL, the leakage reactance, in direct, and leakage reactance in quadrature XL. And you can have RA, RF, RD, and RQ are the resistance of the respective winding. Actually, we developed these circuits in order to simplify the derivation of some time constants and some also reactances, transient reactance. How much XD prime, how much XD double prime, how much XD, how much XF, XD capital, XD small, XQ capital, XQ small, XQ prime, transient reactance in quadrature axis, or subtransient reactance. Now when we have 3 periods for the fault analysis or transient analysis, we can have subtransient period, which is immediately after the fault, and transient and steady state. So we need to find XD, XD prime, XD double prime, and also XQ, XQ prime, and XQ double prime. Sorry, it is opposite, by the way. And this is XD and XQ are the steady state. These are the steady state reactances. Double prime refers to transient. So we need to, based on these circuits, we can approximate how much XD, how much XD prime, how much, and also we can derive the time constants of the field winding. And you know the time constant in general, if you want to calculate time constant, it becomes L over R. So, or X, or the time constant T equal to X over omega R. L equal to X over omega. So we can find the time constant of the field winding, the time constant of the field winding if the armature circuit is open or closed. And several time constants and reactances can be driven based on these in these circuits, as we will see in a few minutes. So the synchronous reactances XD and XQ. This is the steady state. XD and XQ equal to the leakage plus the mutual. Field and Dunbar reactances equal to XF equal to the leakage plus mutual. In steady state, XD equal to also leakage plus mutual, and also for the quadrature X Dunbar winding leakage plus mutual. Transient reactance. Transient reactance XD prime is calculated as such. Based on that circuit, you can write XD prime equal to leakage reactance plus the field and the mutual connected in parallel. And if you can have this circuit, if you look at the circuit from here and you want to get the total reactance, XD prime. When we say XD prime, this is a transient. So this winding will be eliminated. And the effect of the Dunbar winding appears only on subtransient. So this is not there in transient period. It will appear, the effect will appear in subtransient period. So eliminate this winding. So you have XMD and XLF in parallel, and the summation is, or the equivalent is series with XL. So XD prime of the machine will be XL plus XMD times XLF over XMD plus XLF. The time is over, and let us stop here and continue next class, inshallah. So this is XD prime, and we will continue. So XQ prime, we can have the same XQ prime if you look to the circuit from here. So this is the transient, so the impact of this Dunbar winding will not be there. So we have XL plus XMQ. So this is XQ prime. And we can continue later on to find out XD double prime, XQ double prime, and also time constants of these circuits. So if you have any question, please ask. Otherwise, you can leave. Let us stop here and continue next class, inshallah. Any question?